Welcome back, fellow Aquarists, to the second episode of the science of rocks in your aquariums. And if you missed the first part, go watch it, please, because it's the why I'm making this entire series. Today, we're plunging deeper into the waters to try to figure out what chemistry is affected by rocks. Rocks aren't just some pretty ornament you could put in an aquarium. They are chemical influencers, altering the composition of the water that they preside in. Let's kick off the exploration of this by talking about the two chemical properties that are affected by rocks most commonly. The first is pH. pH, simply put, is the measure or ratio of alkalinity or acidity in your water. Certain rocks like limestone or calcite can significantly impact pH. And to show you that, we set up an experiment. I have in front of me 5 different containers. And these 5 containers all represent different things. This first container just represents regular tap water. The next 2 represent different types of calcium carbonates. One being marble, which is a metamorphosed version of limestone. And the second one being chalk, which is a non-metamorphosed version of limestone. This 4th container was home to galena, which is a lead silver sulfide. And then this one is home to a copper carbonate, which is malachite or azurite, depending on what color you're looking at. All 5 of these were left overnight with these minerals in them. And some of them, as you can tell already, are more soluble than the others. If you don't believe me, let's take a look at a graph. These are the end results. I'm not going to get into big statistical stuff or anything like that. I just want you to kind of cognitively think about what these results mean. There's 2 key principles that I think we're going to need to cover so that way you guys can interpret this data a little bit better. The first being, if you look, all of the water that contain minerals in them buffered up to the pH that they're supposed to be at, basically. So for instance, chalk, we know limestone and calcium carbonate buffer up to a 7.9. And so no matter how much time we took, it still buffered up to that pH and kind of stayed there. And then secondly, all of the water that contained minerals were incredibly stable, comparably to tap water. And so we'll get into the why both of these things work in a little bit, but this is just an experiment that you guys can actually see the data sets of whether a rock is going to affect your water or not. With that being said, I'm gonna pass it back to you, Chris. Now, I did this to demonstrate a very large and kind of important point, and that is, just because it doesn't fizz with acid doesn't mean that it won't affect your water chemistry. There is also another problem though when dealing with rocks that contain calcium carbonate. There are, of course, calcium carbonate crystals, which form through evaporation. So like these guys, where they're perfectly shaped and they look so pretty and they're so nice. But then there's also calcium carbonate in these rocks too, where you can't really see them because they're either the main cement or they're not crystalline, right? So what do you do in those instances? Well, so I have this wonderful piece of breccia, or actually I'm gonna say that that's just a very unhappy sandstone, but some of the minerals are starting to fizz because the actual cement is calcium carbonate. This one is a little bit more of a violent reaction, so both of these would contain enough calcium carbonate to mess with your water quality. This is also another distinction I kind of wanted to make as well, but every single rock on this table are corals, either fossilized or old or ancient, either way. These are all extinct animals. Calcium carbonate became the dominant mineral for our ocean, which means all of these fossils will react with acid in some way, shape, or form. Some of them a lot more violently than others. This rock also is made almost entirely out of calcium carbonate, and you can see that it's super pretty, super shiny. To the untrained eye, this could be quartz basically, or some sort of sandstone, but this is actually marble. It is metamorphosed limestone, so an old fossil that was metamorphosed or pressed and heated, basically. And this too, because its chemical composition is calcium carbonate, will react with acid. In fact, it's probably reacting just as much as the fossils do. That's because the composition itself hasn't changed. The actual structure of it has. Buffering capacity refers to water's ability to resist changes in pH. Rocks with high buffering capacity, like limestone, can act as natural stabilizers, preventing very large swathes in pH fluctuations. In some cases, calcium carbonate actually is a good thing for your aquariums, depending on what species you have in your aquarium. Think of buffering capacity as nature's insurance policy, right? You're ensuring your aquarium's pH stays within a safe range, even in the face of external factors. A good example of an external factor in nature would be when it rains. Now, rainwater in itself is slightly acidic due to the nature of it being produced and the way that it is deposited. However, when it rains, acidic minerals like sulfides and organics start to dilute into the water and make it more acidic. This water then ends up depositing into a lake. And so this is a very real example on how these pH buffers work in nature. So let's say we have a lake. This lake has a lot of calcium carbonate in it. And over time, it'll buffer up to a certain pH. And then when any rainwater comes, it will remain stable at that pH until eventually the calcium carbonate all weathers out or chemically dissolves away. By strategically placing these rocks into your aquarium, you can tailor your aquarium water for certain species that enjoy acidic or alkaline water. Specifically things like mollies, live bearers, or even other types of plants like hornwort. Now let's talk about general hardness. General hardness in the aquarium trade and the aquarium hobby is only dealing with the amount of magnesium carbonate or calcium carbonate in a dissolved solution, or in a dissolved state, or in your aquarium, right? But in science, unfortunately, when we talk about hardness, we talk about all dissolved minerals. And I feel like I would be doing a disservice by not showing you how important this distinction is. Future Chris is gonna go to the boards and we're gonna talk about it. So let's take a look at this aquarium. We have a fish, we got a couple other fish, we have some plants, and we have a whole bunch of different rocks. These are just some of the things that are visible in our aquarium, but what about the invisible things like calcium and magnesium, or even carbonate? Well, those are what we would call total dissolved solids, or TDS for short. Now, we can read TDS with a TDS meter, but it also reads all of the total dissolved solids. So what are some of the issues with this? I have 900 TDSs, or total dissolved solids. But we don't really know whether or not those 900 TDS are good or bad. Another aspect we don't know about this is if we have one concentration of an element, how do we know what the rest of it is? So for instance, let's look at calcium. We have 30% of that. We know that that's 30% of calcium, but 60% of what else? So all of this is just a roundabout way of saying that TDS meters are really good at what they do, right? We can use them to figure out how much of things are in our water. But as for the specifics, we need to use other tools like these different types of chemical tests. Both together make a really good substitute. But there is a problem still. We can't test for everything. See, from that explanation, TDS is just a number. It's not something that we actually know of all chemical species within a unit, nor does it actually help us predict what kind of things are happening. See, even if you know how many TDS you have in your aquarium, it doesn't actively tell you the ratio or even how good of a TDS it is. You could have an entire tank that is extremely hard by using malachite or azurite as your main mineral. Is that good for your aquarium fish? No, it isn't. For instance, you can have an extremely high TDS with any carbonate, but you can also have it with malachite or azurite because that is a carbonate too. It's copper carbonate. And so putting copper in your aquarium in that large of a quantity is not really what's best for your fish, but it still shows you the exact same TDS across the board. Sure, total dissolved solids can add alkalinity or lower alkalinity depending on the concentration of them. However, it is not true in the inverse, which means you can have more total dissolved solids, but it will affect pH, but the more pH you have, it doesn't affect your total dissolved solid amount. Again, when we talk about this, we're tailoring our aquariums to the fish that we have and the chemicals to those same fish. So if I wanted to have a molly tank that had greater reproductive events, and if I wanted to have a better population of mollies, would I choose soft water or hard water? Hard water, of course, with a higher pH, which means I should probably think about putting calcium carbonate in my aquarium. Let's get into what makes a mineral more soluble than not. I'm gonna put up a list of principles that you could follow to basically say, this is probably more soluble than not. Mind you, this is not all inclusive. There are some minerals on this list that have no reaction whatsoever with water. However, it is still important to understand these principles when you're going out in nature to try to find your own rocks, because they could save not only your aquarium fish, but also your entire aquarium. So this is the Mohs hardness scale, which we'll put it into perspective for you here. I have a box here, and this box is actually just a mineral, it's a gem. We'll say it's calcium carbonate, which is calcite, right? In each of the corners, we have a calcium cation, and each of these lattices, those are all carbonates. So they are made up of either positive or negative, and the stronger they are more resistant to weathering, which means weak bonds break and weather faster. So what can we use this for? The hardness scale is usually set through 1 through 10, and it contains minerals that are known to have specific hardnesses like talc, gypsum, calcite, fluorite, apatite is number 5, and then K-spar or orthoclase is 6. And quartz, and topaz, corundum, aka rubies and sapphires, right? And the last one being diamond, which is why everybody has that conception that diamonds are strong. Everything that's a 5 and up is very soluble in water, and then everything below that is generally insoluble. And here's some helpful things for you to remember too. Your fingernail is a 2.5 on the Mohs hardness scale, which means it should be able to scratch gypsum and talc. A penny is a 3.5, which means it should be able to scratch calcite, gypsum, and talc. And a steel nail is a 6.5, which means it should be able to scratch all of the 6s to 1, so orthoclase, apatite, fluorite, calcite, gypsum, or talc. Well, thank you guys for another episode of The Science of Rocks in Your Aquariums. I am Chris, and I hope to see you guys soon. If you really like this, please like, subscribe, and share it with the community. Catch you next week.